Rusting is an example of corrosion. It's a redox reaction of metals with the oxygen in the air. It is generally considered an expensive problem when viewed against prevention, maintenance, and replacement costs. As shown in this diagram from your text, iron acts as the anode. The cathode is often inert, or some impurity existing in the iron or deposit into it. Water, say rainwater, combines with the carbon dioxide in the air, forming carbonic acid which partially ionizes, creating the electrolyte. Road salt can also contribute to the electrolyte. The circuit is completed by the iron itself, which transports the electrons. The rusting process is actually a lot more complicated than shown here. Equations at the anode and the cathode can be written in a variety of ways. The net reaction shown here has been simplified. The iron ions and hydroxide ions form solid iron 2 hydroxide, which in turn combines with more water and oxygen to form iron 3 hydroxide, which then breaks down to form iron 3 oxide trihydrate, rust. The rust can flake off, exposing more iron to the rust. Not all metals corrode in the same way. Some metal oxides don't flake off and therefore protects the underlying metal against further corrosion. The costs associated with corrosion has led to extensive research in the area of chemistry. Preventative measures such as coating iron with paints or enamel or chromium or grease, oil or plastic serve to limit exposure of the iron to the air and water. A hole or scratch can break the layer, initiating corrosion underneath. Iron alloys can have similar properties of iron and at the same time be more resistant to corrosion. The cost of chromium, a component of stainless steel, prevents its large-scale use. Iron covered in a protective layer of zinc is called galvanized iron. If the protective layer is broken, the zinc will still protect the iron because it is more readily oxidized than iron. Since the zinc is oxidized before the iron, the zinc or any other material that is a stronger reducing agent is referred to as a sacrificial anode. Cathodic protection involves connecting the iron with a conducting wire to a stronger reducing agent, say a magnesium metal block. The block of magnesium acts as a sacrificial anode, which is periodically replaced as it's slowly destroyed by oxidation. Gasoline storage tanks, hulls of ships, underground iron pipes all need cathodic protection, and so are attached to sacrificial anodes. You should be aware that simply covering iron with another metal can be occasionally problematic. For example, a tin can is a steel can coated with a thin layer of tin. If scratched, the tin, being a stronger oxidizing agent than iron, becomes the cathode, corroding the iron component of the steel faster than it would if the iron were on its own. Electrolytic cells. Primary cells are voltaic cells, electrochemical cells comprising materials and solutions that undergo a spontaneous redox reaction. Secondary cells are electrolytic cells, electrochemical cells comprising materials and solutions that undergo a non-spontaneous redox reaction. In fact, while voltaic cells produce electrical energy as the reaction proceeds, electrolytic cells require electrical energy to make it proceed. Electrolysis, the process that occurs in an electrolytic cell, converts electrical energy into chemical energy, the opposite of a voltaic cell. The redox reaction in a voltaic cell proceeds in one direction. The Daniell cell has an anode where oxidation occurs at the zinc electrode. Reduction occurs at the cathode, the copper electrode. However, if a power supply were added to the external circuit to force the electrons to move in the opposite direction, then the copper electrode will be undergoing oxidation and becomes the anode, while the zinc electrode becomes the cathode as it gains electrons. As you may have noticed, electrodes in this electrolytic cell, as with the voltaic cell, keep their charge designations.